Hello, in this video we're going to take a look at another test for convergence or divergence of a series of positive terms. This is the ratio test. It's a test we'll use quite often when we move into the study of power series and Taylor series. So the ratio test is stated as follows. Let's set summation k equals 1 to infinity a sub k be an infinite series of positive terms, and suppose that we compute the limit of the ratio of the term ak plus 1 divided by the term ak. So this just means some term ak in the denominator, and then the next term, the one after it, ak plus 1 in the numerator, then take the limit of that as k goes to infinity. If we get an answer rho, so the limit must exist, then we can say the following. If rho is between 0 and 1 but not equal to 1, then the series converges. And if rho is bigger than 1, and it could be infinite, then the series diverges. And we have one case where no information comes across. That's if rho equals 1, or if that limit in star does not exist. Then this tells us nothing, and we have to move on to some other technique, maybe integral test, maybe comparison test, maybe something else, to decide whether the series converges or diverges. So let's look at a couple of examples here. So first one, let's determine the behavior of the infinite series summation n equals 1 to infinity. In the numerator, we have 1 times 3 times 5, and then a bunch of dots, 2n minus 1. In the denominator, e to the n, pi to the 2n, n factorial. So let's start by just asking, what does this numerator mean here? So you're going to see expressions like this now and then. And this numerator, 1 times 3 times 5 to 2n minus 1, it just is the way we denote the product of consecutive odd numbers from 1 and finishing with the odd number 2n minus 1. So for example, if n were equal to 6, you're looking at the sixth term of the series, that the number would look like this. You'd have 1 times 3 times 5. You keep multiplying odd numbers till you get up to the number 2n minus 1, in this case 2 times 6 minus 1. And of course, since that's 11, that would denote the product 1 times 3 times 5 times 7 times 9 times 11. So the product then of the first 6 odd integers. So it's kind of like a factorial, but you have all those even numbers missing. So we're going to run the ratio test to determine whether the series converges or diverges. Ratio test is often good when you see lots of products like this, factorials, powers, etc. So we have to, first of all, write out the ratio. What does an plus 1 over an look like? Now the way I like to do that is this. I write the denominator first. The a sub n, that is just the term you see in the series. So if you erase the summation sign, what's left is a sub n. So here's our denominator. You can see that all I've done is just taken that term of the series and put it in the denominator down there. Now, to get a sub n plus 1, you replace every n down here with n plus 1 in the top. So instead of e to the n, we have e to the n plus 1. Instead of pi to the 2n, we have pi to the power 2 times n plus 1. N factorial gets replaced by n plus 1 factorial, etc. And even this n in the 2n minus 1 down here gets replaced by n plus 1. We have 1 times 3 times 5, and we finish up at twice n plus 1 minus 1. Now we're going to have to do some algebra with this thing, reduce it before we can take the limit. And the way I like to do these things is often, we have to do some invert and multiply here, but then bring together the like terms from the top expression and the bottom expression. So for example, I've brought together the e to the n over e to the n plus 1. When we invert and multiply, this e to the n down here goes in the numerator. So I've paired that with the e to the n plus 1 in this denominator. Likewise, pi to the 2n pairs with pi to the 2n plus 2. And n factorial inverts to come above the n plus 1 factorial here. And then finally, in the numerator, we have 1, 3, 5, this product of odd numbers till we get to 2n plus 1. because twice n plus 1 minus 1 is 2n plus 1. And from the denominator, we just get this term. So if you lay things out like this, it's often very easy to see the cancellation and how you're going to make things work. Now, when I do the cancellation in this first term, remember this is, the top is a product of all odd numbers up to 2n plus 1. So the odd number 2n minus 1, it appears right before this one. So when I start canceling 3s and 5s, etc., I know eventually this 2n minus 1 down here will cancel with the 2n minus 1 just before it. And so we're going to see the result when all things are canceled, that leading fraction becomes a 2n plus 1. Then there'll be the other stuff from these other fractions. And what happens there, it's not hard to see that the e to the n over e to the n plus 1, make that division, we just get e. Pi to the 2n over pi to the 2n plus 2 leaves a pi squared in the denominator down here. And n factorial over n plus 1 factorial. Remember, n plus 1 factorial is equal to n plus 1 times n factorial. And so in that sense, the n factorials cancel, very much like what happened in this initial fraction up here. Now, this limit is not hard to compute. There's a lot of constants, and we pay attention to the n's here. Those are the dominant terms. We're left with 2 over e to the pi squared. It's an impressive number, but all that we care about is the fact that it's less than 1. And so that limit being less than 1 tells us that the infinite series, that's right up here, converges by the ratio test. Here's a slightly different sort. Here we aren't going to have the terms given to us immediately, but sometimes there's a relationship between one term of the series with the next. So let's look at the infinite series summation n equals 1 infinity a sub n. And suppose the terms are defined this way. They're defined recursively. We're told a1 is 5. And then after that, we can get each successive term an plus 1 if we know the one before it, a sub n. We're told an plus 1 is n squared over n plus 1 squared times a sub n. And we'll delve into this a little more deeply later in this example. But right now, let's run the ratio test on this example. So although we don't know what the terms are, this is really set up to be a pretty easy ratio test. So let's set that up. We have the limit as n equals infinity, an plus 1 over an. We're going to just do the following. We're going to take the a sub n and just leave it down there. And now for an plus 1, though we don't know exactly what that is, we do know whatever it is n squared over n plus 1 squared times a sub n. And of course, once the a sub n's cancel, we end up looking at the limit of n over n plus 1 quantity squared, and that's equal to 1. Now, that's, of course, the rho equals 1 is the no information case of the ratio test. So this is no help to us, really. We cannot tell whether the series converges or diverges. Okay. So no help. And so we have to do some other work and maybe apply another test. Now, it's probably useful in other work with comparison test, integral test, etc., if we want to use those, to know a little bit more about what those a sub n's are. So let's work them out, see what this recursion is telling us. So here's the recursion we're given. Here's how you get an plus 1 if you know a sub n. And we know a1 is 5. So the recursion works like this. Suppose you want a2. Well, a2 is a sub 1 plus 1. And so that is the n equals 1 case in this recursion. And so if I put in n equals 1, I get 1 squared in the top, 1 plus 1 squared in the bottom, times a1, which is 5. And this all comes out to be 5 over 2 squared. To get a sub 3, similar thing, a sub 3 means a sub 2 plus 1. So that's this recursion now, but with the n equal to 2. And so if I put n equals 2 in the recursion formula over here on the right, I get 2 squared in the top, 2 plus 1 squared in the bottom, times a sub 2. That gives us 2 squared over 3 squared times a sub 2, which was 5 over 2 squared. And we get 5 over 3 squared for a sub 3. So try working out a sub 4 and a sub 5. You should find you get 5 over 4 squared, 5 over 5 squared. And as is often the case in this subject, don't be in too big a hurry to multiply things out. In particular, notice I've left this as 5 over 2 squared, 5 over 3 squared, 5 over 4 squared, even 5 over 5 squared, which you could make 1/5. But often if you don't multiply things out, we see patterns like this a little better. And so with this information, pretty easy to guess what's going to be happening here with this, this idea about these various square terms canceling each time we do these recursions. It looks like pretty good guess is that a sub n is 5 over n squared. So that tells us the following, evidently that this mysterious series summation a sub n, where the a sub n's are generated this way, is really just a tricky way of writing summation n equals 1 to infinity of 5 over n squared. And that is known to converge. It's a convergent p-series with the p equals 2 bigger than 1. So here's an example of how if we use the ratio test and that ratio rho turns out to be 1, we might have to go on and look at another test. So what to remember? So if we have a series of positive terms, summation k equal to a sub k, the ratio test says look at this ratio. Again, be a little careful in forming this ratio and taking its limit. Don't want to make a mistake there. But when you do this limit, if it exists, the answer is going to be somewhere between 0 and infinity. And most of that is good news. If the limit's less than 1, the rho is less than 1 convergence, rho greater than 1 divergence, and if rho equals 1, no information, you got to go try something else. The series could converge, it could diverge. Don't guess, try something else. Now, the ratio test usually fails anytime you have a series that is the ratio of two polynomials, like let's say pk over qk, k running from 1 to infinity. So you'll find that, and you'll do some examples, but if you have things like this, and there are some other forms too, you'll always find the ratio in these cases with p and q polynomials, the limit of the ratio turns out to be 1, and so you're going to have to use some other test, probably a comparison test or integral test in these cases. And then finally, we didn't discuss it in this video, but noted in the book, and this is very important, we'll use this a lot in the power series and Taylor series chapters or sections, that if the ratio test fails, rho bigger than 1, I shouldn't say fails, but if rho is bigger than 1, the ratio test, then of course, again, we know this series diverges. But in fact, with a little more work, and we'll see some of this work in another video, with a little more work, you can show that if this happens, then actually the a sub k's are going to infinity. So in other words, the limit of a sub k as k goes to infinity, in this case, is not equal to 0. And so actually this is really an nth term divergence test case. We saw earlier that if the terms you're adding up are not getting small, not going to 0, then the series diverges. So the moral here is when a series diverges by the ratio test, it really diverges because you're adding things that are getting infinitely large. So on that happy note, we'll bring this video to an end. Thank you.